label those two graphs as either C being greater than 1 or C being between 0 and 1. Should be a snap, snap. If it's increasing, what do you know about C?
See it and be like, I know that.
Yeah. Now, there's exceptions if there's been transformations done. But if it's just your base graph, y equals c to the x, that's the only choice you can have. Right? That base has to be greater than 1 for the increasing, and between 0 and 1 for the decreasing. Okay, so properties. We talked about this. For this particular function, the y-intercept is always 1. The x-intercept, there isn't an x-intercept. Horizontal asymptote, the equation is y equals 0. It's the x-axis. Domain is all real numbers. I'm not going to put all the squiggly notation. And the range is y greater than 0, not greater than or equal to. Okay? Because of that asymptote. So be careful on that. Common mistake to put that in. All right, so here are some transformations that we're going to apply. So we learned all of these. Horizontal translation, vertical translation. Right, so the horizontal is with x, so that's going to add or subtract in the exponent. Vertical, just like other ones, you can show it with the y, or as a separate constant term if you solve for y. Reflection in the y-axis, we change the sign of x. Reflection in the x-axis, we change the sign of y, or again, solve for y, leave it about front. Horizontal stretch, x is replaced with ex, so this is a horizontal stretch by 1 over b, right, when we have that coefficient there. Vertical stretch, replace y with y over a, means we solve for a in front. So if it's in this form, that is your vertical stretch.
Okay, so because then you have the negative exponent, it's just 1 over c to the exponent, which is the decreasing version.
That's right. Yeah. Okay, so now I'm just going to turn this on so we can. Okay, so would any of these transformations affect the domain? If so, which ones? So the domain is all real numbers. Do any of those change all real numbers? No. If the domain was like a certain amount, then obviously if you do a translation or a reflection over the y, that would change. But it's all real numbers, so it stays all real numbers. No. Would any affect the range? Well, now we have a limited amount. The original range is y greater than 0. Would anything horizontal affect that? No. So we want to look at the vertical things. Okay? So if we start with y greater than 0 and we translate it down or up, will it still be y greater than 0? No. Okay, so that one, it affects vertical translation. I'm just going to use abbreviation. Reflection on the x-axis. So if this is going up like this, and I reflect in the x-axis, now it's going to be below it. So that's changed the range. So that is going to affect it. Will the vertical stretch affect that? Okay. So that's it. Now, specifically, the horizontal asymptote. Now, remember, the horizontal asymptote has the equation y equals 0. Okay, so if I vertically translate this up or down, what happens to the asymptote? It changes too, right? So yes, vertical translation. If I reflect this in the x-axis, does that change their horizontal asymptote? No. It stays there. So that one's not going to do anything. And the horizontal asymptote is on the x-axis. And remember, under a vertical stretch, anything on the x-axis doesn't change. So the vertical stretch is not going to affect the horizontal asymptote. So that is it. Okay, now specifically, the y-intercept. So this base graph is 1. If I translate up or down, is it still going to be 1? Nope. If I reflect on the x-axis, is it still going to be 1? Nope, it's going to be negative 1. If I stretch it, is it still going to be 1? No. So those ones, and then the stuff we have to think about horizontal as well, actually. Vertical stretch. Okay, so those make sense. Horizontal translation. So this was my point on the y-axis, 0, 1. If I translate this 3 to the right, this would be 3, 1. What would then be over here? So it would be basically move everything to the right. So now I have a different y-intercept. So a horizontal translation will also affect the y-intercept. Okay? A reflection in the y-axis won't, because it's on the y-axis, and a horizontal stretch won't, because it's on the y-axis. Okay, but those all vertical and a horizontal translation. Okay. So remember, the y-intercept can always be found by substituting x equals 0 into the equation. So if you're not sure, always just substitute it. Okay? All right, so what transformation must be performed on your base graph in order for the transformed function to have an x-intercept? Okay, so what can we do? Yeah. So vertical translation. Okay, and that's really it. I mean, you can have more than that. You can stretch it as well, but a stretch alone won't do it. A reflection alone won't do it. You've got to vertically translate. Yep. Oh, yeah, show it. Sorry, down. Yeah. Or if you do more than one, yeah, reflection and then reflection will do reflection and upward. Yeah. Now there's a single transformation. It would have to be a vertical translation. Yeah. Right across the x-axis. Okay, so let's get we have a summary here.
Oh, you caught me. I wasn't able to make fun of the mistake anymore.
Okay, so that's not the transformation form. Remember back to the transformation unit, when it's in transformation form, all the transformations with y are on one side and all with x are on the other. This is close to transformation form. It's been solved for y. Okay, so we actually mostly show it like this, just like with trig functions. We usually show it as y equals. In any case, you can see what all the transformations are. It says the domain, well, for exponential, it's always all real numbers. So if a is greater than 0, right, so that means a is positive, so that's your stretch, and it means there's been no reflection. Then the range is what? So think about that. What's the range going to be for that transformed function? Normally, it's y greater than 0. Yes, y greater than k, because it hasn't been translated, so it may have been stretched, which is still above the x-axis, but then k's been added on. K is positive, will be above, k is negative, will be below the x-axis, but in any case, it's always going to be y greater than k. And if a is less than 0, that means it's been reflected, then untranslated, so that's going to be y less than k. You know what? Look at that. I feel at lunch and my neck started to feel better. It's so good. Oh, maybe it's the math. Maybe it's the math. Oh, it's starting to feel better. Nice. Okay. Equation of the horizontal asymptote then is y equals k. All right, state the equation of the asymptote and the range. So, it's always going to be a constant term, provided this has been shown in a form where you can tell what the base is, x is in the exponent, right? So in this almost transformation form. So that is going to be y equals -3, y equals 7, y equals 0. Right? Then your domain is based upon that. If the a value is positive, it's going to be y greater than the k value. I'm not going to put the squiggly brackets for this. Okay. Then if the a value is negative, then it's going to be y less than the k value. So here, less than. Okay, back to the transformations unit, right? Describing your transformations. You do it in every unit. So now, this is our new graph. This is our original. So you can see your base of your exponent is the same. Now we have a 6 in front and -2x. So vertically stretched by a factor of 6 about the x-axis. Horizontally stretched by a factor of, remember, we don't incorporate the negative. Coefficient is -2, so we take the reciprocal of the 2. And then reflected about the y-axis. We're changing the sign of x. Okay. Horizontal asymptote, there's no k value, so it's going to be y equals 0. Y-intercept, remember, we can substitute 0 in for x. If there's nothing added to x here, then it's just going to be this coefficient of 6, right? Because think about it, 1/3 to the exponent -2 times 0 will be 1/3 to the 0. Anything raised to the exponent 0 is 1. 6 times 1 is 6. But if there's a translation, remember that can affect the y-intercept. Okay, so if there were no translations, then the equation of the exponential function is in this form. Then the equation of the horizontal asymptote is y equals 0, and the y-intercept is a. Because a lot of our application questions are going to be like this, with nothing added or subtracted afterwards. So that's why it's kind of signaling that one out. So y-intercept, you put 0 in for x, you're just going to get 3, coefficient. 0 in for x, makes that exponent equal to 1, that power equal to 1, so y-intercept is 2. Make that 0 in for x, make that the power equal to 1, so y-intercept is -5. Okay, pretty easy. It says verify with your, oh no, sorry, not quite yet. transformations unit. Coming up with a new equation. So we're given our original one, y equals 2 to the x. It's vertically stretched by a factor of 3, horizontally stretched by a factor of a half. It's reflected, translated. So write the equation. So A is our vertical stretch. Then we've got our C here is 2, right? Horizontally stretched by a factor of a half makes that B value positive 2. Reflected in the x-axis changes the sign of y, so that's going to be negative 3 there. Translated 1 left, so bracket x plus 1 and 5 up. Plus 5 after that whole power. So, equation of the asymptote, look at the constant, y equals 5. Domain, always all real numbers. Range, y. Now, we have to decide if it's less than 5 or greater than 5. This reflection means it's now below the x-axis. When you reflect it, and then you're moving it at 5, so it's everywhere below 5. Now the y-intercept is not going to be negative 3 here, yeah? So, how this compares to the last one we were doing, this has translation stuff. So that's going to change your y-intercept. Right? It's not just the negative 3 here. So in this one, I would probably, just to be safe, substitute 0 in for x. And then you can do the rest in your head, right? So 0 plus 1 is 1, 2 times 1 is 2, 2 squared is 4, negative 3 times 4 is negative 12, plus 5 is negative 7. And then you can graph it on your own time and check for your y-intercept. Okay. You're going to be so good at transformations at the end of this course. Okay, so now mapping notation. Again, your base graph is y equals 2 to the x. So describe in the correct order. Remember, you write stretches first, then reflections, then translations. Maybe I'll go back to full screen here. So you're changing the sign of x, which means you're reflecting in the y-axis. Okay, and then translation. So horizontal translation 1 right, vertical translation 3 down. Remember, mapping notation, it is what it is. Okay, whatever numbers are there, that's what we do. Okay, so find the image of 3, 8. stay stuck under those transformations. So you don't, yeah, just follow the transformations. So horizontal stretch, vertical stretch, reflect in the y-axis, and then translations, one right and three down. So if you have this, remember you can just substitute those values in there. I went through each step, but if you put 3 and 8 into your mapping notation, you will get your image point. But you do not want to come up with your transform function and then put the x value of 3. That will give you a point on it, but it won't be the image of 3. So, vertical stretch by factor of 1/4. Your C here is 2. Horizontal stretch by factor of 2, so that will be 1/2 as the exponent, x minus 1. Oh, what about the reflection in the y-axis? That's going to be negative 1/2 times x minus 1, and then 3 down. Try your best to make those exponents small. I've seen some of your writing. Okay? Try not to. You have to distinguish what's your exponent compared to your base. Okay? So maybe you have to write really big in your base. Something that you can't. So I often see, like, I'll see something like that. Well, I know what I'm looking for, so I kind of know that that's probably going to mean that's an exponent. But it could mean, maybe you mean 2 minus 1/2 times x minus 1, right? So make sure that you are trying your best to show an exponent as a smaller, what do you call that, subscript, I guess. Superscript, yeah, subscript. Okay, verify the equation using the image point from B. So we said here that -5, -1. So that means my left side would be -1. My right side would be 1/4 times 2 to the -1/2 times -5 minus 1 minus 3. And evaluate that. So 1/4 times 2 to the exponent. So that's going to be -6 times -1/2 is +3. 1/4 times 8 is 2 minus 3 is -1. And I'll leave the calculator part to you on your own. And then question 7 is kind of a really interesting one in a sense. Something that probably you'll be asked on some type of an assessment, whether it's a test or cumulative. Okay. Alright, so 7a is something that we talked about with quadratics back last year. So example 2, 4 lies on y equals x squared. If it's transformed to the graph of y equals 4x squared, then we can either talk about it as a vertical stretch by a factor of 4. So if we did that, the image of 2, 4 would become 2, 16. Taking that original y value and multiplying it by 4. Okay? But if we consider it to be a horizontal stretch, well, why would we do that? Well, we could show this, did this back in Math 20. We could replace the original x here with 2x. When we square that, we get 4x squared. So we get the same simplified function, but our transformation was we replaced x with 2x. So that's a horizontal stretch by a factor of a half. So when we do that, our original point becomes 1, 4. Okay, you can tell these are points on the graph, but they are different. That doesn't mean your image graph will be different. It just means the image of that point will be a different value. Both of these will be on your graph, right? It's the same graph, y equals 4x squared. It's just the image of a certain point is different depending on which transformation you're doing. But you still get all the points. Okay? It's just something to be aware of. And that then leads into an exponential. Same kind of thing can happen. A vertical stretch of an exponential can sometimes give you the same graph as a horizontal stretch or translation. Okay? So it says 0.38 lies on the graph of y equals 2 to the x. If that is transformed by a single transformation here, okay, then we can obviously, looking at it, this looks like a vertical stretch by 8. So if we did that, our original point of 3, 8 would become 3, 64. If we consider that a vertical stretch. Okay. So, then the hint on this next one, Adam, are you doing any work or are you just playing golf? You done everything? Okay. Horizontal translation. So, this is your original. Horizontal translation means we add or subtract something to x. Okay, we still have to get y equals 8 times 2 to the x. So my hint is doing what we did yesterday with your power laws. How can we express 8 with a base of 2? Exponent 3. I'm just going to put it underneath here. Y equals 2 cubed times 2 to the x. And then using your grade 9 power laws, that's 2 to the x plus 3. Okay? That function is the same as this one. Just a different way of showing it. Okay? So, by showing it this way, we can see, we can translate y equals 2 to the x, to the left, 3. Okay? In which the point 3, 8 on the original would become, well, we would subtract 3 from 3, it would become 0, 8. And you can tell, you put 0 in for x, you get 8 for y. Okay? So, a horizontal translation can also be shown as a vertical stretch. Remember that. Okay? And then let's do question 8. Maybe we'll leave question 9 for today. So look at the next one. Practicing a little bit of function notation because, again, back in that function or transformations unit, struggled a little bit with that. So as you can see from the previous examples, different transformations corresponding to different image points can produce the same graph. Although both answers are correct, we'll often use the one that is most obvious or least complicated. Okay, so this one we've got f of x equals a quarter raised to the exponent x, it's transformed into g of x, okay? Where g of x equals 32 times f of 3x plus 4, your function notation. So g of x equals then 32, f is this, where you replace this x with 3x plus 4. Function notation. Then it says, write g of x in terms of h of x. So now we've got a new function. H of x is equal to 2 to the x. So we have to now take g of x and somehow get it down to having a base of 2. Well, this I can show with a base of 2. 1/4 is 2 to the 1. Negative 2. So I can show that with a base of 2, and I can simplify it all. Okay, so g of x is now going to be equal to 2 to the 5th, 2 to the negative 2, and 3x plus 4. And use your power laws to simplify that. So I've simplified it down to a power of 2. I'm still not quite done because it says I need to show g of x in terms of h of x. H of x is 2 to the x. So 2 to the negative 6x minus 3 will be the same as h of negative 6x minus 3. So g of x equals h of negative 6x minus 3. Okay, so that then tells you what transformations can be applied to h of x to get g. Okay?
Would you prefer us to isolate the x or do
when we're doing this part?
factor it out? Like
Oh, in this, doesn't matter. Okay? In the next part, you do need to, in order to know those transformations. So from here, remember in transformations, we like to have the coefficient of x in the brackets being 1, so I need to factor out negative 6, which actually makes that 1/2. Okay. So what does that mean? That means a horizontal, I'm just going to abbreviate, horizontal stretch by 1/6, reflection in y-axis, because I'm changing the sign of x, and horizontal translation left half a unit. You know what, let's just do 9 so that we're done the whole thing. Number 9 is probably done, you may have done even like experiments in science class. This kind of thing, right? Setting out a hot substance and then recording the temperature over time. Will the temperature of that tall 2-cup no foam extra hot latte or mocha ever get colder than room temperature? No. Okay? It will never. It will approach room temperature. Okay, so that's why it can be modeled. The change in the temperature of it can be modeled with an exponential function, because it'll decrease a lot. That's when I have to go across the hall to use my board frequently. Keep it hot, but it will decrease quite a lot, and then it'll get close to that room temperature and kind of just stay there. Okay, so it's an exponential function. So here is this particular model. So capital T is the temperature in Celsius. Lowercase t is time in minutes. It says use your graphing calculator to sketch it. So let's do that. We haven't used our calculator much. Okay, so 80. If you have a fraction, you can use the fraction t, or you can go x for t divided by 4. That's good eyesight. Okay. I'm done now. Okay, then my window setting, 0. We're not going back in time. Maybe, well, I'm not sure. Let's go 20 minutes, 0 to 20. See what happens. 1 by 1s. And then your y min. Well, what do we know that based on this equation, the temperature of the environment or the room is approximately 15, right? It's that constant term, degrees Celsius. It's a little bit chilly, but okay. So you could go y min be 15, or you could start at 0 if you wanted to, but 15 is going to be the lowest it will be. And maximum would be 80, right, when t is 0. Oh, no, not 80, sorry, 80 plus 15. So 95, we'll put 100. 100's boiling, right? Okay. So it's, you can tell it's curved. It's not a straight line. Okay? And it's going to take longer. So my window, maybe I'll go to 60 minutes, 1 hour. So the initial temperature when the pot is set on the counter, remember I initially said 80, but then there's the 15 on it, right? So, or in your calculator, 0 would give you 95. Okay, because of that vertical translation. 80 plus 15 is 95. Temperature of the room, we just said, is 15. Okay, and then you just use your calculator. So determine the temperature of the coffee to the nearest tenth of a degree, sitting for 10 minutes. So trace, just punch in 10, that's your x value. And that's going to be nearest tenth, 50, actually 54.0. And then vice versa, to cool to 20, that's when, on your calculator, you graph y equals 20. Okay, and then intercept that's gonna be, what is it, nearest tenth of a minute, 38.6. Okay, so that's the end.